Before we finalize this chapter, I would like to talk about 4 different methods that we have covered so far. And I would like to talk about what should be the thought process to decide which equation we should use. So these methods were lump capacitance method, semi-infinite objects, spatial solutions with approximate series, and exact solutions. So what happens? So ideally the simplest solution is the lump capacitance method. So first, based on the geometry that is given to you, you calculate the BO number. And if the BO number is less than 0.1, you go with the lump capacitance method. This is the easiest method, and we have solved this. We have solved multiple examples on this one. So that is number one choice. If it is not a lump capacitance problem, so if you are dealing with very large scale object, so it is most likely that you are dealing with a semi-infinite object. And semi-infinite objects, we have 3 cases, and we talk about the solutions for these 3 cases. I'm going to re-summarize them in a moment. So that is our second choice. If we don't have a semi-infinite object, and if the BO number is not less than 0.1, then we will look for spatial effect solutions where we are only considering the first term, single term. So this is only applicable if the Fourier number is greater than 0.2. Of course, if you don't know the time that you are trying to find, you need to assume it is initially greater than 0.2 and then try to solve it and confirm your assumption. And so that is our number 3 choice. And if none of these work, then you need to go through exact solutions. So you need to have infinite series solutions. We talk about these. Or you need to use numerical methods and apply nodal networks. So in the lump capacitance method, the first step was the calculation of the BO number. And BO number is calculated in terms of the critical length, which is defined as volume over surface area, which is experiencing convection. So we already have the solutions given, and we derive all of these actually. So these are the solutions for lump capacitance method. And if you have a semi-infinite objects, we have 3 cases. We just talked about these today: constant surface temperature, constant heat flux, and convection boundary condition. And the solutions for all 3 cases are given here. And if first 2 cases are not applicable, then we'll assume the system satisfies this condition. And we have 3 cases again: a planar wall, a cylinder, and a sphere. So in this case, so the definition, so in this case, we have Fourier number and BO number, and the definition of the BO number is different for this spatial effect problems. It is not LC, it is HL over K for a plane wall and HR over K for cylinder and sphere. Okay, it's important to remember the definition for the BO number that will allow you to find C1 and zeta 1 from the tables are different. Okay, the definition of BO number is different for the spatial cases. It is not HLC over K. This is not correct. BO number is not for finding these constant. Okay, the definitions are different. And again, so if Fourier number is greater than 0.2, we only consider the first term. These are the first term series solutions. Okay, and if you are interested in temperature in the middle here, so x equal to 0 or r equal to 0, these are going to be all 1. So all of the solutions will actually behave the same. All of the solutions will be the same. Only difference is these constants will be different. So constant zeta 1 and C1 will depend on the geometry, obviously. And the BO number, again, is defined this way. It is not defined in terms of LC. It is defined with respect to L here, or it is defined with respect to R. and R for cylinder and sphere. And if none of the three cases work, then we need to go through infinite series, and infinite series solutions are given in here. And again, the definitions of the Biot number for finding these constants are given here for different